Let's get started. This is the last talk of this parallel session. We're going to have a talk now by Michael Bremner, Ashley Montanaro, and Dan Shepard. And Michael's here to present on average case complexity versus approximate simulation of commuting quantum computations. Michael?
Okay, thanks, Krista. Thanks, everyone, for coming. These are parallel sessions. You have a choice to be here or not, and you've made the choice to be here, which is great. Yeah, thanks to the organizers for organizing this really great conference in this amazingly beautiful location. And I really have to stop just looking out over the mountains and thinking, like I want to look out there rather than talk about this. Anyway, so this is some work I've been doing with Ashley and Dan over the last few years. Ashley is based at the University of Bristol, and Dan works for the UK government, and I work at University of Technology Sydney, which a lot of you went to last year for QIP. So I don't know how you guys feel, but I mean, personally, I think it's a really exciting time to be working in quantum computing at the moment. And a big part of that is the experimental progress which has happened in the last few years. For a long time, working in this field, it was like, you have conversations with experimentalists and be like, hey, what can I do with like a 2-qubit gate? And you'd be like, tomography, some other stuff, do the gate again, do it twice, do it 3 times. But finally, we're getting to a point now where experimentalists are actually asking the question, what can I do with 20 qubits? What can I do with 30 qubits? What can I do when I have a universal gate set over a large number of very large systems? And so we're getting to a point now where the things they can do are actually beginning to become really theoretically interesting. And one of the questions they're always asking is, what sort of computations can we do, or experiments that we can run that really demonstrate that our devices we're building go beyond something a classical computer can do? There's a lot of things you can do, and a lot of things that people have been progressing towards. People have been working hard on building gates with very high fidelity. Another thing that they're looking at doing is to perform error correction. People regularly try and run small instances of Shor's algorithm on their devices. More broadly, people are looking at the problem of what quantum systems can I simulate with the large engineered quantum systems that they actually have access to. And then you've got the approach that D-Wave and others have taken, which is to say, okay, let's instead focus on sort of other problems that we think are probably hard that we can sort of efficiently check in our computer. And hope that it doesn't turn out that those problems are easy. Okay, so the overall challenge is really to identify quantum computations that are in some sense post-classical, and even more so to identify the simplest quantum computations that are also post-classical. So doing quantum computing experiments is really, really hard. We want to make it as physically simple as possible to show experimentalists how to build quantum supreme devices, or devices which demonstrate quantum supremacy. Okay, now the problem with this is that we don't even really know how to identify quantum computations that are post-classical. Right now, it's still very much an outstanding question, if we're looking in the time complexity sense, as to whether or not quantum computers can be classically simulated or not. So we have to confront this question, and hopefully you also get an answer which allows, turns out to be, attractive for experimentalists. So, as most of you would all know, Aronson and Arkhipov took a great step in this direction a few years ago with their discovery of the Boson Sampling protocol. Okay, in the Boson Sampling protocol, the Boson Sampling protocol has many of these features. You can make a very strong complexity theoretic argument that it is not that these Boson sampling circuits are not classically simulable, while at the same time, they're relatively physically simple. Physically simple. What is the protocol? Well, it's pretty straightforward in one sense. This is a picture I took from Jeremy O'Brien's, the O'Brien group's recent paper that was published in Science, where they ran a Boson sampling experiment on 6 photonic modes. Okay, so how does Boson sampling work? You input single photon states into a linear optical network, and then you measure in the number basis. You're working in a regime where there's very low probability of getting a photon in any given mode has been getting 2 photons in any given mode, so you basically get bit strings out of this protocol. Now, the linear optical circuit that you're implementing, which is going to be classically hard, is randomly chosen. And there's a bunch of reasons as to why that's the case. Okay, so what Aronson and Arkhipov actually proved that if a classical computer could simulate this sort of process to within L1 norm distance in polynomial time, then a bunch of things happen. So the polynomial hierarchy would, well, they conjectured that the polynomial hierarchy would collapse in this case. So the answer is more or less that you cannot approximate these systems in classical polynomial time under 3 conjectures. The first conjecture is the polynomial hierarchy is infinite. We kind of have to take that as a given. So as Adam talked about on Tuesday, the polynomial hierarchy is kind of like a generalization of P versus NP problem. It's widely believed that this thing is actually infinite. These results imply that if there was a classical simulation of linear optics, then it's not. Okay? And that would be very, very surprising to complexity theorists. But they have to make 2 other conjectures, which are actually really vital to the argument. The second is that the permanent anticoncentration conjecture is true. And the third is the Gaussian permanent approximation conjecture is also true. Okay, so what have we done? We've improved on this result in a number of ways. Firstly, we have come up with an argument that works very naturally in spin systems. So the Boson sampling argument is actually quite particular to linear optical circuits. And while you can simulate linear optical circuits on a quantum computer, the cost in doing that is very, very high. So something which looks quite simple, like just doing non-adaptive linear optical circuits, is quite simple in optics. Well, simple. It's very complicated to simulate this on a quantum computer. What do we actually show? What we show is that if the average case complexity of multiplicative approximations to either the complex temperature Ising model partition functions or the gap of degree 3 polynomials is sharp B hard, then quantum computers cannot be efficiently classically simulated to within a constant additive error without a collapse in the polynomial hierarchy. As I said, this improves on the Boson sampling protocol by proving the equivalent of the permanent anti-concentration conjecture. And as to why we can actually prove that will become apparent as I go through the talk, but basically it comes down to a lucky guess about the choice of circuits in which we examine. Now, the other interesting aspect of our work is that our techniques are really quite simple, and it's very likely that there are other conjectures you can form which imply the classical hardness of other sets of quantum circuits. Okay, so let's actually talk about the circuits that we've analyzed. So the first sort of post-classical family are those that are generated by random Ising, what I call random Ising circuits. All right, so the Ising model is a ridiculously frequently studied model in condensed matter physics. And it should be familiar to, I guess, most of the people in the room, but for those who it isn't, what you have is, say, some graph of vertices, okay? On each vertex, you're going to have a spin. The edges on the graph represent an interaction between those spins, and on each vertex, you're also going to have some sort of self-rotation kind of term. All right, so the actual Hamiltonian, you can write this graph is basically just describing a Hamiltonian. The Hamiltonian is as follows. So between the edges, you're going to just have an XX interaction, coupling spins, and then on individual qubits, you're just going to have like an X term. Okay, so the class of circuits that we're interested in come from evolutions according to random instances of the Ising model. Okay, so what do I mean by random? I mean we're going to randomly choose these edge weights and these vertex weights from the complete Ising model graph. So, you draw a graph which interconnects every single qubit in your system, and then you're going to randomly assign edge weights. Sometimes those edge weights will just be 0, which means there's no interaction between those 2 qubits, and sometimes it'll be something else. Specifically, we've chosen these edge weights just to take weight between 0 and 7. Similarly with the vertex weights. And what we show is that, and then we're going to sample from evolutions according to this. So it's a circuit that looks like this. Okay, we put a pi over 8 outside our Hamiltonian here, so that's sort of for time pi over 8 this Hamiltonian is evolved by. That choice is just useful for connecting this to another class of gates, which I'll show in a second, but is relatively arbitrary. Okay, so what's the actual hard, the classically difficult thing to do? Well, you prepare these circuits, and then you're just going to sample on the computational basis from the output of these circuits. And you're going to have to do this, say, polynomially many times. And what we actually prove is that if conjecture 1 is true, then there is no efficient classical algorithm that can sample from any output probability distribution R of x such that it is within a constant one norm bound from the output probability distribution of this circuit. Okay. This is equivalent. So these sort of evolutions turn out to be equivalent to randomly choosing circuits composed of T and square root of control Z gates. So you'll see here we have that's the square root of control Z gate, that's control Z gate, that's a product of 3 square root of control Z gates. So you're just going to compose products of these things. You're going to get at most 7 in order to go around to end up getting the identity of these guys. So we're going to start with, applying a Hadamard's to every qubit, perform the Z diagonal computation, and then perform Hadamard's on every qubit. Okay, we have another family of circuits which are also, we argue, is classically hard. And these are related to the degree 3 polynomials over F2. And just very quickly, these circuits are ones which you basically generate by randomly choosing this diagonal bit to be from the set of Z, control Z, and control Z gates. Okay, physically they're a bit less nice because you have to do 3 local gates, and experimentalists freak out when you talk about that. Each one of these circuits can be related to a degree 3 polynomial over 2, where the random choices of, say, the CCZ gates correspond to, putting a 0 or a 1 up here. Similarly for the control Z gates and the Z gates. And so sampling from the circuit is actually equivalent to sampling from the Fourier transform of that function. And we have another conjecture, which is independent of the previous conjecture, which is that if conjecture 2 is true, then there is no efficient classical algorithm for sampling from this class of circuits to within a constant one norm bound. Okay, so one of the reasons why these classes are interesting is because of the implementation of them. Okay, the Ising circuits, that first class of circuits I talked about, like I said, they're drawn from a complete graph on n vertices, which is a little bit ugly from a physics perspective because you have to do, well, if you're constrained to doing Ising type gates, you have to do long range gates. Okay, so you're going to have to potentially interconnect every qubit in the system, which is again scary for experimentalists because we don't live in like an n-dimensional world. However, so you can show that the class of circuits we're talking about require on the order of n squared gates, and there are 2 local Ising type gates and they can be long range. If you have access to a universal gate set and a lot of ancilla qubits, you can parallelize these circuits down to within log depth. And that's based on really old work in quantum computing from like 1998 by Chris Moore and others, where they showed that any sort of 2 local commuting, or any commuting circuit composed of k local gates can be parallelized down to order log depth. Now say you're constrained to a 2D lattice, which is what most experimentalists are constrained to, then you can actually show that by a lot of parallelization again, that you can implement these sort of circuits in order n depth, which is pretty good. It's not super great, but it's pretty good to get it down to order n depth. So another aspect of our work is that our results imply that with high probability of randomly choosing these Ising circuits will actually lead to a circuit which is classically difficult to simulate. Okay, so this is a really important feature of our work in that most arguments about the classical difficulty of a given quantum algorithm talks about individual instances of problems. Okay, you need to know which is the hard instance. In our case, our argument is implying that actually most instances are going to be hard. So you can be satisfied by just sort of randomly generating a few of these circuits and then implementing them. And finally, I've already said this, but it requires circuit accuracy to only constant variation distance. And this is where things are actually, this is the thing we have to do the most work to actually prove. Why are such additive bounds essential? Because if you have finite gate sets, any sort of like noise model which is physical, and you also want to in any way sort of learn the states that you're actually making, you need to have these sort of proofs work to within additive bounds, which means we have to work pretty hard. Now, those of you who've been around for a while might be saying, hey, didn't you like give this talk 5 years ago? Because this is all sounding really, really, really familiar. So if you went to Adam's talk, you would have heard a lot about this earlier in the week. About 5 years ago, we were sort of looking at similar questions, except what we were able to show were similar statements, instead in terms of multiplicative error bounds over your output probability distributions. And as I just said, these things are kind of unphysical, and it's kind of unsatisfying in a sense. However, where these sort of bounds are really useful is for classifying problems you might hope to be hard to simulate classically. Okay. And it's worth actually emphasizing that it's very unlikely that every multiplicatively quantum supreme circuit is also going to be additively quantum supreme. I'm kind of overusing this quantum supreme thing, but I feel like I should. It's very unlikely these two classes of things completely overlap. And that's due to the difficulty of actually satisfying this additive error requirements. All right. So one of the most common questions I get when talking about this work is, why can't I just simulate this awesome system I have already instead of doing something like this? Well, the problem comes down to actually really proving the complexity. That it's quite hard to categorize the complexity of physical systems. I'm not going to go through all this, but just to give you a sense, you can kind of define problems which are related to your quantum mechanical system, and it's quite hard to narrow down a problem which you can be relatively guaranteed that the thing you're going to build is classically hard to simulate, or not classically hard to simulate, and that's really the main challenge here. What we exploit is that there is sort of an asymmetry between certain counting problems and their classical and quantum hardness. So a natural class of problems which upper bound quantum circuits is these sort of gap P and sharp P hard problems. This class of problems, I should have said on the previous slide actually. So if you wanted to look at the difficulty of evaluating the exact, the difficulty of computing a quantum amplitude in a quantum circuit, you tend to find that this problem either lives up here or it lives down inside P. So for the Clifford circuits, for the right sort of inputs, you can show that you can evaluate these amplitudes down here in P, whereas for a very wide range of other circuits, you can show that the worst case complexity of computing that amplitude is going to be at least sharp P hard. In fact, it's kind of worse than that. It's actually a class called gap P, which is slightly more powerful than sharp P. It's a generalization of sharp P. Now, gap P complete problems are really interesting in that they have this property that under multiplicative approximations, so that's an approximation that looks like this, they stay gap P complete. Or at least, at the very least, they stay gap P, sharp P hard, depending on the reduction you have. Okay, whereas functions which live inside sharp P end up having an approximation inside the polynomial hierarchy under multiplicative approximations. So this is a result that was shown by Stockmeyer way back in '83. And they showed that any function sharp P can be approximated to within a constant factor with high probability inside BPP to the NP. Okay, and that result uses basically the fact that, well, this result is actually yields an algorithm for computing these approximations to sharp P hard problem, or sharp P, for problems that are inside sharp P. And it uses sampling over the output states, or output solutions to these sort of, well, to classes of circuits which yield sharp P hard problems. Okay, so this brings me to sort of Aronson and Archipel's great idea. They noticed, or they knew about this difference between gap P complete problems and problems that are inside sharp P. Okay, and they, well, formed the idea that, maybe we can show that if classical circuits can simulate quantum circuits or linear optical circuits, then you're going to be constrained to live inside the class of problems that live down here. typically. And then maybe we can leverage Stockmeyer's algorithm to show that, in order to get an argument that linear optical systems can't be classically simulated. So what they actually show is that if you could simulate linear optics classically, and if you have a BPP to the NP machine, you might be able to use Stockmeyer's theorem to compute complex matrix permanence, which is a gap P hard problem, which is related to linear optical systems. And I guess the really big insight they had is if you use random quantum circuits, this isn't ridiculously hard to prove. Okay. As I said, the complexity of this problem comes down to this class of problems, these gap P hard problems. Okay. So Fortnow and Rogers and also Fenner et al. Showed in 1997 that gap P complete, that evaluating quantum circuit amplitudes is a gap P complete problem. And with a little bit of work, you can show that this implies that evaluating the output probability of a quantum circuit can in principle be sharp P hard. Okay, and what do I mean by this? And how do you see this? Well, what they show is that so gap P problems are those which count the difference between the number of accepting and rejecting solutions of an NP problem. Okay, and so what you actually get out of these problems is like some number, delta C, which can be a positive or negative number, and they show that by you can encode